Hi everyone, this is about summary of chapter 32 and 33. Chapter 33 is about electromagnetic waves. It describes the light propagating in the medium. First thing I'd like to explain is the generalized Ampere's law. I have briefly explained this in chapter 29, and this is to explain how a AC current transmits through a capacitor. We discussed about the AC current passing through a capacitor in chapter 31. And from the Gauss law, the electric field flux, which is electric field through a surface, is equal to, if it is closed, it is equal to the total charge within a surface divided by epsilon zero. So the total charge within a closed surface can be obtained by multiplying epsilon zero with the electric field flux out of the surface. Right. So if we consider a closed surface which encloses one of the capacitors or plate, then the electric field only exists between the two capacitance plates, and so the electric field flux out of this half sphere surface is only the electric field through within these two plates. So if we define the electric field flux, then by the definition of current, which is dq over dt, should be equal to epsilon zero d over dt electric field flux. So if we define this as a capital psi E, which is the electric field flux, then we can define the current equals to epsilon zero d electric field flux over dt. So this is a displacement current we defined before, and that's the extra current through the surface. And from the Ampere's law, which is the magnetic field line integral, is equal to mu zero times the current within the surface, passing through the surface. So if we put the displacement current into this equation, we have the mu zero I enclosed, that's the physical current passing through the surface, and the next term is the electric field flux passing through the same surface. So modified Ampere's law becomes that the line integral of B field is equal to mu zero times the physical current passing through the surface plus 1 over c square electric field flux, derivative of electric field flux through the surface. 1 over c square is nothing but epsilon 0 times mu 0. That's the constant. And this is the 1 over square speed of 1 over c square. That's the 1 over speed of light square. Compared to the Faraday's law states that electric field line integral is minus d over dt magnetic field flux. So this term, magnetic field line integral, is equal to 1 over c square. The electric field flux over dt is quite similar to the Faraday's law. So if there is no physical current, this equation is almost same as this equation except for 1 over c square. So right. So in this case, modified Ampere's law, if there is no physical current, we have this situation, and this is the cross section of a capacitor I have discussed here. If there is a uniform electric field, if electric field changes, it generates magnetic field. So modified Ampere's law states that if there is a time variation of electric field, it generates magnetic field. It is the opposite of the Faraday's law. If there is a change of magnetic field, it generates electric field. So if we calculate the magnetic field as a function of radius, we obtain exactly the same shape of magnetic field by the change of electric field flux as a function of radius. If there is a uniform electric field but its magnitude changes, then we have this generated magnetic field, and this generated magnetic field is proportional to 1 over r. If small r is larger than r. So this 1 over r dependent magnetic field is like the magnetic field by a current line source. So this implies that even though there is no physical current, we can generate magnetic field. That's modified Ampere's law. Similarly, if there is change in magnetic field, it can generate electric field. So these two equations, one is the Ampere's law in free space, and Faraday's law in free space is very similar, and it states that change of electric field can generate magnetic field, and change in magnetic field can generate electric field. Even though I cannot mathematically derive the wave equation because it is a little bit complicated and above the contents, the level of contents we can cover in engineering physics, but these two phenomena states that electric field change can generate magnetic field, and magnetic field change can produce electric field. That's how electromagnetic wave propagate in vacuum or in free space. So if we change magnetic field or current through this kind of circuit, we can generate electromagnetic wave traveling this way. And this is the reason how we can generate or transmit signal with an antenna through the medium, through a free space. And electric field and magnetic field have a right angle, and this is how the electromagnetic wave propagate through the medium. I cannot derive mathematical expression for this, but this is what happens based on the modified Ampere's law and Faraday's law. So next we can mathematically express the electric field as sine or cosine wave along the j hat. J hat represents the y direction unit vector, and b is k hat. K hat represents the z direction unit vector. So we can mathematically derive the electric field and magnetic field has a right angle and have the same phase with respect to distance or time. And since electromagnetic waves are waves composed of electric and magnetic field, we have previously derived that for a capacitor, the energy density of the capacitor is proportional to 1 over 2 epsilon 0 E square. Electric field is the electric field between a capacitor. For a solenoid, if there is a magnetic field within a solenoid, the energy density of solenoid can be represented as 1 over 2 mu 0 B square. So these energy densities represent the energy density of electromagnetic wave traveling through a medium. So that represents the energy density, which is energy per unit volume. And the Pointing vector, that's the energy flux, is can be derived as 1 over mu E cross H. So that's the Pointing vector, and the physical meaning of Pointing vector is the flux of energy through a medium. So except for the physical meaning, I'll just skip this part. That's all I can discuss about in chapter 32. Energy density of electromagnetic wave is same as the energy density of a capacitor plus energy density of solenoid. These are the expressions for energy density of capacitor and energy density for a solenoid. And based on that, we can derive that the flux of energy becomes 1 over mu 0 E cross H. And I will not derive this. And the propagation of light is about chapter 33, and there are several things you need to remember. First thing is the refractive index. Speed of light in vacuum is C becomes lambda 0 times F. That means lambda 0 is the distance of a wave for one cycle in distance, and F is how many times it oscillates. So for each oscillation it travels lambda 0, and F states how many oscillations there exist per second. So lambda times F, it's by its meaning becomes the speed of a wave. If lambda is the period for each cycle, and F is how many cycles there exist per second, so lambda times f becomes the speed of any wave, especially for a light. C is given as a constant, which is 3 times 10 to the 8 meter per second, and it becomes lambda 0 times f. So for a given frequency of light, lambda 0 is given because C is given. So wavelength of light in vacuum is represented as lambda 0. Frequency of light is given f. And if it travels through a medium, the frequency of light does not change, but the wavelength of light changes to lambda equals lambda 0 divided by n. N is the refractive index. Refractive index of many materials have different numbers. These are just numbers. For a vacuum, n becomes 1. And for a lot of oils and the ethanol, it has 1.3 and 1.5 and so on. Water, for example, has a refractive index of 1.330. For typical glass, fused silica, it has the refractive index of 1.45 and 1.5 and so on. So the light within these mediums, the speed of light is reduced by C over n because f is same, but lambda is reduced by lambda 0 over n. For example, in water, lambda of a specific frequency is reduced by 1.3, lambda 0 over 1.3. So speed of light is reduced by refractive index n, and the lambda is reduced by refractive index n as well. So that is the two things you need to remember. And there is a famous Snell's law. I can derive it, but it's difficult to derive it within a college, the engineering physics level. So you need to remember this. N1 sine theta 1 is equal to N2 sine theta 2. N1 and 2 are the medium, refractive index of medium, and theta 1 is the angle, normal angle from a surface normal to the propagation direction of light. So this is theta 1 and this is theta 2. And the relation between N1, theta 1 and theta 2 and N1 and N2 is satisfy this relation, and this is called Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. There are two important concepts you need to remember. First one is critical angle. And if you increase theta 1, that is the refractive index of, for example, this is water and this is air. The refractive index of air N2 becomes 1, and 1 is 1.3, and if N2 is 1, sine theta 2 cannot be larger than 1. But if as N1 is 1.3 times theta 1 can be larger than 1 for a certain angle. That certain angle is the critical angle. That means if theta 2 becomes pi over 2 based on this Snell's law, this one becomes N2, and that's theta 2 means theta is the angle with respect to the normal surface normal to the propagation direction for this one. So if this is the right angle relation for theta 2, when theta 2 becomes pi over 2 or 90 degrees. So if there is a critical angle theta c. There exists a theta c where the theta 2 becomes 90 degrees. That's the critical angle. That means there is no light transmitted through the second medium. That only happens when N1 is larger than N2. For example, this is water and air, and this is a glass to air. There is no critical angle if theta N1 is smaller than N2. That means air to glass transmission, there is no total internal reflection, critical angle. And total internal reflection is the condition where theta 2 becomes 90 degrees. That means all lights are reflected. No transmitted light exists. And that's when the initial refractive index of the medium for the input beam is larger than refractive index of the transmitted medium. So that's called critical angle, and no light can, 100% of light is reflected from the surface. And this is the condition where we use in a fiberglass, glass fiber, optical fiber. And second thing we need to remember is the polarization. As I mentioned, electric field and magnetic field have right angle for an electromagnetic wave, and we define the polarization angle of light for the polarization angle of electric field. So we can think about two possibilities. Unpolarized light have two electric field components, but polarized light has only one electric field component. That is called polarized light. For a special case, if we have an angle theta, theta b is the reflected light, and that's also same as the input angle, and theta r represents the refracted light, so that's the transmitted light. If the input and output theta angle, if the input angle plus output angle becomes 90 degrees, that means theta r, sine theta r is sine 90 degrees minus theta input b. Then by the relation of sine and cosine, it becomes cosine theta b. 90 degrees minus certain angle sine function is equal to cosine of the angle. So from the Snell's law, it is n1 sine theta b is the transmit input beam, and n2 sine theta r is the transmitted light. Then, as I just derived, sine theta r becomes cosine theta b, so I can rewrite sine theta r as cosine theta b. Then this is cosine theta b and sine theta b, so if I divide this on both sides with cosine theta, then it becomes tangent theta and n1, n2 divided by n1. So tangent theta becomes n2 minus divided by n1. So this is the Brewster angle condition, where theta b, tangent theta b is equal to theta 2 over theta 1. So for a special case where the input beam angle and output beam angle, addition of input beam angle plus output beam angle is 90 degrees for a specific polarization whose electric field is oscillating like this. There is no reflected light, so perfect transmission happens for a polarized light is represented with a green arrow, and there are some reflected light for a polarized light whose electric field is coming out of this screen. So these are the two concepts you need to remember. Critical angle is given like this. There is no light transmitted. For a Brewster angle, there is no reflected light for a electric field which is polarized along the green direction, arrow direction. That's a perfect transmission or total transmission, whereas there is total reflection for the critical angle, and there is a total transmission for a Brewster angle. And total transmission only happens for a polarized light it is oscillating, whose electric field is oscillating with the green arrow direction, and this is called P wave. And the orange electric field for light whose electric field is oscillating along the orange direction, that is called S wave. And Brewster angle only happens for a P wave. You need to remember this one. That's about the content of all the materials about chapter 32 and 33. That's it.